Good afternoon, everybody. Today will be the last lecture for three-phase, and we'll be done with the revision of single-phase and three-phase. And then we'll start working on the topics in the electric machines. But it was very important to review this concept before we start, because we have machine single-phase, three-phase. If we don't review it, so we'll have a problem in the future. Today lecture is not a big one, because I want to make sure that you understand how to find the capacitor that will correct the power factor, because really it's an important topic, how to improve the power factor. So I'm going to explain power factor correction in a three-phase system. And we're going to use a nice formula. And I know we did the quiz last time, so when I look at the solution of all of you, so I understand now what I'm supposed to do, so it'll make you do it in an easy way. Usually you have the transmission line, and then you got three wires. And the load is a three-phase. You might have one load, two load, three load, doesn't matter. You have many loads here, so that represents the load. And usually the load is inductive load. And you connect every phase to the load, so it can supply the power. We suppose that we can find the power, total power of the load, reactive power, power factor, and also we can find the complex power. So everything should be known, and according to theta, because if you know power factor, you can know the theta of the load for a three-phase. When we need to correct the power factor or improve it, so we'll connect in parallel capacitor. In a three-phase system, we're going to connect three capacitors across the load. So we might do that. We'll have between this phase and this phase capacitor C, and between this phase and this phase another capacitor, same value by the way, and there is one between the first and the third. So you have three capacitors between each line. So the question is, if we want to improve the power factor, let's call it was the old value power factor 1, and we like to improve it to power factor 2. And power factor 2 is better than BF1, which means that it's getting closer to 1. It means that the value is getting bigger of the power factor. It's a ratio, it's bigger. And theta is getting smaller. There is a formula, because what happened to the capacitor? The capacitor is going to provide the load by the reactive power. Reactive power, Q. That's the main goal. And I will remind you that if that is the let's say that this is the load, that's the power, call it P1 and Q1 and theta 1 and S1, and accordingly the power factor 1 is equal to cosine theta 1. And we want to improve it from theta 1 to theta 2, or from power factor 1 to power factor 2. So what we're going to do, we're going to add a capacitor. The capacitor will go in the other direction. Observe that that's the Q of C. Observe that the Q will be in the opposite direction, and the power does not change. Why the power doesn't change? It's the same. You have idea why the power is constant, doesn't change? If you add the capacitor, it only affects the reactive power, does not affect the power. Why do you think? Or do you think it should affect the power? It shouldn't. Just say whatever you expect. The first question, do you think the capacitor should change the power? Yes? Why?
Because it's allowing more current to pass, so you would think there'd be less current and voltage, coming at the same time.
Okay, but there is something. He said something good. That I mean, the current from the capacitor is going to affect everything. But there is something. We know that the current is not only magnitude. Any current in AC, it's like a vector, has a magnitude and a direction. So there is a real part, you can call it IR, and another part is called IX. It has two components. So what do you expect? The capacitor. The capacitor does not have resistance. So it's only supplying reactive power. So the current is not in the real direction, not in X direction. It's always J. It's always perpendicular, as you see. So it's not going to affect the power. The power of all stored energy elements, as you know from the circuit 2, is equal 0 for inductors and capacitors. The only power produced by resistor. So that's why it will not affect the power, because it's only supplying the active power. It doesn't have anything to do with power, with active power. Secondly, that's good. Well, lucky it doesn't affect the power. Why? Because the power, this is the real active power that the consumers consume. They consume the active power. So if you affect it, you will be upset. For example, you are turning on your light, you are consuming, say, 1,000 watts, then the capacitor come and then make it 800 watts. You will not be happy. You need to consume the power that you want to consume. And that's good, by luck, that's good. So yes, the capacitor only affects the active power, and it will be in the opposite direction here. So what is the resultant? You subtract this line upward minus QC, you'll get the new Q, which is Q2. So say that's, it will come here, because this part is equal to QC. So that's what's left. That's Q2, the new one. Accordingly, you have a new angle, theta 2. You have new power factor. So our task now to find what is the value of QC that it will improve our power factor. That's the first task. What is the value of QC? Obviously, QC is equal Q1, the old reactive power Q, minus Q2, the new. So that's with the old one, the bad one, and that's the new one after the improvement. So QC will supply the difference between both. That's QC. You can calculate Q1. You can calculate Q2 because you know from the part triangle, if you have S, P, Q, and theta, so what is the relationship between Q and power and theta? Q over P is equal to tan theta. Accordingly, Q is equal P tan theta. So what is the value of Q1? Now we can do it. Q1 is equal P1 tan theta 1, the old theta, minus Q2. Q2 is equal P2 tan theta 2. And we said, well, lucky. P1 is equal P2. Power doesn't change. So I can say P1 equal P2 equal P. So I will take P as a common factor, and what's left? Tan theta 1 minus tan theta 2. That's QC. So that's the amount of the reactive power required from the capacitor to supply the system to improve the power factor. But remember, we are working now with 3-phase. If we are working with single phase, that's fine. That's QC for the capacitor. But what about when we have 3 capacitors? So this QC is not going to be supplied only by 1 capacitor. They're going to be supplied by 3 capacitors. And we need to find the value of each capacitor. So what should you do? You divide this 3-phase Q by 3. It gives you only the Q required for 1 capacitor. But just I want you to pay attention. If you're working with single phase, whatever you got here, that's the amount required by the capacitor. If you're working 3-phase, you got to divide it by 3. So that's QC let me just write here 3-phase. So QC for single phase, it will be P tan theta 1 minus tan theta 2 divided by 3. That will be the QC required for each capacitor. Okay. Once you get the value of the reactive power required from each capacitor, it's an easy task to find the value of the capacitor. Why? Because we know there is a relationship between reactive power and the element itself. It's either capacitor or inductor. I'll refresh your memory. Q is equal V squared over X in general, XL, XC, or I squared X. I'm talking about the single phase. What about 3-phase? You just you will have 3 times this one. And also, let me just write also power. Power can be found as V squared over R or I squared times R. That's for phase. If you want 3-phase, multiply by 3. Obviously, the capacitor here is connected between each line across the lines. So I will use the voltage one, because the voltage across the capacitor, it's the same as the voltage across the node. Look at the voltage here. That's the voltage between this node and this node, between this line and this line. It's the same voltage applied to the capacitor. So it's better to use V squared over X, not using I squared X. So you might ask, when can I use I squared X? If they are connected in series. Because when you connect 2 elements in series, the current will be the same. So I will use I squared. If they are connected in parallel, I'm using voltage, because the voltage is the same across both elements. So I'm going to use this one. Accordingly, I can find X. And I'm talking about XC. So I'll say XC, and that was the quiz last time. XC will be equal to V squared over Q. V squared over Q. Which Q? QC. Because I'm getting XC. I'm getting for each capacitor. So QC should be only for 1 phase. And already I did that. When you do that, you get XC. Remember, this formula only valid when you are using root mean square values, not maximum value. So let's say that the voltage here should be root mean square. What about the current? The same thing, root mean square. All these equations based on root mean square. And that's, a normal practice of electrical engineering. So once you found XC, you can find a capacitor. Why? We know capacitor. What's the relationship between the capacitive reactance and the capacitor? XC is equal 1 over omega C. Accordingly, C is equal to 1 over omega XC. And omega is equal to 2 pi F. So C is equal 1 over 2 pi F, and you have XC. So that's how we get C. If you want to put this formula with this one, substitute by XC in the equation, you can get one formula for finding C just in one shot. So you have C equal 1 over 2 pi F, and XC, 1 over XC will be the opposite. So QC will come in the top. Because, yes, because 1 over XC will be equal QC divided by V squared. So you have QC in the top, and you have here V squared, and don't forget root mean squared. So that will be the formula for finding the capacitor. Depends on the calculation of QC. Well, if you wanna make it, I mean, more, you can put this formula QC in this equation and you get one just formula. You program it and then you can get it. Q is equal P tan theta 1 minus T theta 2 over 3. Or you want to keep it separate, that's okay. But I have to write next to it. QC is equal 1/3 or P over 3 tan theta 1 minus tan theta 2. Check, yes. So that's the way. So that's how to find the capacity. Do you think if I give you a quiz now, again, on this one that I did last time, you will be able to do it? You have the equation. If you have any question, ask me. Then I will give you one problem, 10 minutes, you'll do it, just to apply. So yes.
So that equation for QC right there, is that for a three-phase?
No, that's the equivalent phase, because I divided by 3.
Okay.
If you didn't divide it by 3, that will be the 3-phase. Any question? You ready? Okay. You can write the formula with you, both of them, and just try. The same system I just sketched, balance load connected, that's the information of the load. 240 connected to 240 kilovolt root mean square, 60 hertz. The power is 90 kilowatt, and the power factor is 0.727 lagging. We like to improve the power factor to 0.9 lag. The question is, what is the capacitor used? Find that. That's exactly just what we explained. It's a direct problem, just to, I want to get used how to use the formula, how to do it.
Oh, that's voltage versus power. So the first one is voltage.
Yes, voltage. And usually the voltage giving like that is line to line. Yes.
If I use my phone as a calculator.
Yeah, go ahead. Yeah, you can use anything. Yeah. Even if you want to use MATLAB, that's fine. I'll give 1 more minute. Write your name. So it was a direct application to the formula that we just did. Okay. No more submission because I did line finished. Now we'll go to another topic, and I'm going to post the solution on the folio because there's nothing in it. I'm going to substitute by the same values, but I will show you how I do it in folio system. So now I want to learn how to measure the power because we're going to use it in the lab. There are 2 methods to measure the power in 3-phase system. One method using 3 wattmeters and another method using only 2 wattmeters. So what's wattmeter? So wattmeter is just something to measure the power. The structure of this wattmeter from the side, if you look at it, has 2 windings. One winding for the current, another winding for the voltage. So sometimes you call it coil. So this coil for measuring the current, and of course it has like a polarity, that's a positive, and that's the negative, and this is a positive, and that's the negative. So if you have load and you want to measure the power across the load, let's say that this is load. So you connect that in series, and that's the supply. So the current coil is connected in series with the load to measure the current. And the one, you can call it the voltage coil, will be across the load in parallel. So there's one point connected here and another point will be just connected there. And it will give you the direct measurement power. Like what when you did experiment 1 in the lab, you find there's one just give you the power, P, Q, S. So that's the structure of the wattmeter inside. 2 coils, one for the voltage, one for the current, and then they do the calculation inside, they multiply. So if we say that the voltage phasor is equal V magnitude, and let's say root mean square on angle theta V, and if the current is equal to I root mean square and the angle theta I, so the power in this case will be equal to VRMS times the magnitude of the current IRMS, and the angle will be theta V minus theta I. Why? Because we take the conjugate. Theta V minus theta I, you can call it theta in general just to make it simple. So that will be the, let me just make this clear. That's not only the part, that's S. So if you want to find the part, find the real part, will be cosine theta. And theta is equal to theta V minus theta I. So that's the part is going to be measured by the wattmeter. When you have a three-phase system, you use three. That's the old method. So let's just sketch. You have a load, and you are going to do this experiment in the lab next week. So that's the load, three-phase, and there are wires coming out connected to the supply. So how you measure the power? Using a 3-watt meter. Well, you put three each on one line. So let's just put one here, one there. That's 1 watt meter. Call it W1. Second one, and the third one. And you got the old coil for the current, you connect in series. And the positive should be where is the current flowing in. That's the positive. You have to look at the polarity. And the voltage would be in parallel. So there is one here, second, third, and what you're supposed to do, you get all these wires and connect them together. So that'd be how you connect the 3-watt meter. So this method, we call it 3-watt meter method. And the total power going to the load will be just the sum of all of them. P1 plus P2 plus P3. And that's three-phase load. You will do that in the lab. You calculate the power, the Q, the power factor, and the steps will be very clear. And then you will do the same thing using 2-watt meter methods. They found out that 2-watt meter method can be used with just adding simple calculation, and then you save one. So let's just have the load three-phase here. So that's three-phase load. Doesn't matter delta or star. And we're going to have only 2-watt meter. Three lines coming here. Supply. That's phase A, B, C. So we're going to use phase A to put the watt meter. And that's the first one. It's called W1. And how you connect it, the same thing. Just in series will be the current coil, and the voltage just will have one here. And this one we're going to connect it to phase B. What about the second watt meter? That's the watt meter. It has the coil of the current, the same thing in series, and the positive sign should be here because the current should come from the supply towards the load. And the voltage coil, let me just make it bigger. That's the coil of the current, and that's the coil of the voltage as usual, and that's the wattmeter itself. So you take this one and you connect it to the same point here. So it's like the voltage coil of both. They are not measuring phase. No, they are measuring line to line, line to line. That's how, I mean, it will help to find the total power. That's what meter 2. Now, how can we calculate the power? The power was measured by 3 wattmeter. We add P1 plus P2 plus P3. You just add the 3 readings. This one you have only 2. And this one measure P1, P2. But there is difference between this method and the other method. This one, the voltage coil, it's across line to line. So to find the power, the total power supplied to the load, it's equal to the sum of P1 plus P2. And it is proof the same. If you do the equation, line to line voltage, line to both of them, you'll find the same thing. Q is a little bit tricky. The total Q, you are going to subtract P2 minus P1. And pay your attention. P2 coming from W2 or wattmeter, second wattmeter, which is connected to phase C. And the first one connected to phase A. And then when you subtract the power multiplied by root 3, you get the total reactive power supplied to the load. So if I make a triangle, just to make it simple, that's the total power. P1 plus P2. And that's the Q. Root 3, P1, I mean P2 minus P1. And that will be the S total. And that will be the total power factor for the load. You make this triangle make it easy. Observation, that's the Q. That's the P total. Q total, by reading P2 and P1, I'm going to ask you now, what happened if P1 is equal P2? P1 equal P2. What does it mean? It means there is no reactive. Reactive is equal, Q is equal to 0, right? What does it mean for the load? Not efficient. It means the load is no. That's the Q is equal to 0. The capacitor reduces reactive power. The inductor consumes reactive power. But the resistor, no reactive power. So it means the load is resistive. It means the whole load, I mean, just only consists of resistance, nothing else. Because Q is 0. And the resistor does not produce or consume reactive power. What happened if he found that the Q is positive, or in other words, P2 is bigger than P1? Inductive load, that's right. Why? Because we agree that when Q up, that's inductive. That's for the inductor. When Q down, negative, that's a capacitor. So when P2 greater than P1, so just let's make this observation. If P2 is equal P1, the load is a resistive load. If P2 greater than P1, it means Q would be positive, so it means it's inductive load. And if P2 less than P1, it's capacitive load. To calculate power factor, we already have the triangle, power triangle. It'll be easy. So the power factor here would be equal to cosine theta, which is equal to PT divided by ST. If you find theta, it's 10 minus 1 QT over PT. Just use the old trick that we used before. But just keep in mind, PT is equal, or the total power equal to P1 plus P2. Q total will be equal to P2 minus P1 radical 3 times radical. Let's see if we have time. Yes, we have time to do one example. Using 2 wattmeter method, The reading was like that. P1 was equal to 1560 watt, and the second reading was 2100 watt. When connected to a delta connected load, we have load, and the load is connected as delta. That's the load. And these are the lines here. If the line voltage is 220 volt, that's the line. Nothing is mentioned, it means it's root mean square, but just let me write for you here, that's root mean square. Calculate. We need to find per phase average power. B, per phase reactive power. C, power factor. D, the phase impedance. Using two wattmeter methods. The first question is easy. Do you want to find the average power? How the average of per phase? So what should you do? First, I get the total power in three phase. How you find total power in three phase? As we explained here, PT is equal P1 plus P2, right? So that's what I'm going to do. I find total power. I'll say that the total power is equal to P1 plus P2. That's 1560 plus 100. That will be give 36.0 watt. That's the total power. And when I say total power, for three phase, but the question is per phase. So you say that power per phase just divided by 3. So you have 3660 divided by 3 will give you per phase power, which is equal to 1220 watt. Okay. Second question, per phase reactive power. I'm going to use the formula. I subtract P2 minus P1 times square root of 3. So second one, Q total will be equal to square root 3 P2 minus P1. So square root 3 P2 is equal 2100 minus 1560. That will give 935.3 bar. I want to per phase. That's easy. You will have in the next lab, the pre-lab will be exactly applying this, what we're doing now. So it will be easy for you. That you divide it by 3, the total. So you have 1/3 times 935.3. That will give you 311.775. That's the reactive power phase. What else? Power factor. Okay. We agree that it's better just always to have our triangle here, power triangle. And I put here the power total, or the total power is 3660 watt, and the reactive power, I'm taking, of course, everything here, 935.3 bar. Okay. So to find the power factor, first I get theta. Theta is equal 10 minus 1, 935.3 divided by 3660. Somebody might ask, can I use the per phase quantity? It's the same, because if you divide by 3 in the top and the bottom, it's the same. So you get the theta. It's be 14.33 degree. Once you got theta, you can find now power factor. is equal cosine theta. That will give you 0.9689. Should I write lagging or leading? Should I write lagging or leading for this power factor? Lagging. Why? Because Q is positive, right? I got Q positive when I did subtract. I got it positive. That's right. Lagging. Yes.
Can you scroll up a little so I can see?
Yes, I will do. I will do. But just let me. Okay. I want to do that. I'll make sure to make the last one for the times up. Is up. Okay. So the last question is find the impedance. Almost the angle that you got in the part triangle, the part triangle is similar to the impedance triangle. So it would be the same theta. I'll give you a hint and you can complete at home because the time is up. To find the impedance, of course, you find it per phase. Any impedance, it's equal the voltage by current. So all what you try to do, find the voltage per phase and current per phase and divide them. That's what you're supposed to do. Remember, that will be all vector. What does it mean? If you assume the angle of voltage is 0, that's fine. You can assume that the voltage here, magnitude and angle 0. But what about the current? It will be the magnitude and has angle. Theta I. This is 0. Theta I. What is the theta? This is the same you got from the power factor. The same one, because the triangle of the impedance exactly like the one of the power. So it's the same theta you're going to use. It will give you the value of the theta, and then you divide, you get Z. I'll give you the answer so you can check if you got it right or wrong. Z, the impedance, it's equal 38.44, and the angle is equal 14. The same angle, by the way, 33. So try to do it at home and see if you get the same answer. Any question?